Don't forget. And let's share the screen here. All right. So I think we're in chapter 6 today. I did push the homework due date off until tomorrow by request of some people. So that is available for you. Till tomorrow. Now, let's see what we've got here. Starting in chapter 6. Jason, if you want, there is this computer up here not being used today. The guy that normally sits there is not going to be here. So if you want to jump on there, you can use that computer. You do have to turn it on. The button's on the left side on the back. Actually, you can see it from where you're at. If you push that button there, it'll be starting up for him. There you go. And password is this. All right. And for anybody else who had the free trial going for MATLAB, if you're trying to figure out how to pay for that or whatever, you can come in and use my computers to do homework. I will be here in the classroom most days. So if you want to come in and use these computers, you're more than welcome to. It's a good idea to just call and make sure that I'll be here during the time that you're available to come in and want to work on them. So I can make sure to be here and make sure to open the doors even if I'm out and about doing things around campus. You can even come in and work on your programming while I'm in class. I'm in class Monday, Wednesday, Friday from 9 to 11. And then I'm here from 11 until 1 usually as well, just doing things. So Monday, Wednesday, Friday in the mornings, I'm pretty much around all morning. Tuesdays and Thursdays, I teach in the afternoons from about 12 to about 4. And you can also come during those times, or you can come Tuesday, Thursday morning. You just have to tell me so I make sure that I'm here if you need to use the computers in the classroom. So, moving on to chapter 6. Let's open up MATLAB. We'll need that. Chapter 6 is about user-defined functions. And so this is the beginning of writing actual programs. You've learned enough of the syntax and the built-in functions in MATLAB and how to mess with matrices and how to give some output in the form of plots and things like this. You've learned enough of that we can now begin to use those things within an actual program. And there are different levels of programs. One of the kind of the basic levels of programs is the user-defined function. In some programming languages, they call these objects. I like the name function better because it describes it better, I think. But a function is just what it sounds like. It's just like a function in MATLAB where you have the sign function, for example, where you put in a particular number into the sign and it calculates the sign of that number. It's something that you plug something into, it does something to that thing that you plugged in, and it spits out something. And you can plug multiple things into it and it can spit out multiple things or a single thing and whatever. You can put in one thing, it can spit out multiple things, whatever. It's entirely up to the user who's defining the function. but this is kind of the most basic kind of program that you might write in MATLAB, the user-defined function. So we are going to create a function that is very much like the functions in MATLAB, like the cosine function. This is starting on page 207. So the cosine function has a call sign or a name for the function, COS in this case, and it also has the parameters of the function, the things that you plug into the function. And so for the cosine, if you put in help cos, you will see that if we go to the reference page for it, for example, you can see that in the different examples that they use, they're plugging a number in for x, or they're plugging in an array of numbers into cosine for x. You can also do some other things with this, if I remember correctly, maybe not. I think that's about it. You can do with it now. I'm thinking about it. But anyway, it has particular things that you can plug into it. The types of things it accepts and that allows you to plug in are essentially numbers or arrays of numbers, a matrix of numbers of some kind. Our functions will be similar to that. They will have a name to them, but we will give them their name. Because it's a user-defined function, we decide the name. But it will also sometimes be called in a similar way as MATLAB functions. Like the cosine, you might have to plug some things into it in parentheses if we decide to do that. But also there are some functions in MATLAB you don't have to plug anything into to get something out. And so you can actually create a function that doesn't require any input. Either way, functions usually do have an input. It's kind of their main definition, but it's not absolutely necessary. And you can also, just like we could do this, we could say, let's say that we're going to say flight or something equals the cosine of 9 or something like this. You can actually you can assign the answer to a function, the output of a function, you can assign to a name. You can give it a variable name and save it in your workspace, just like anything else. So you can, it doesn't, and it's not going to matter if it's a function we build. If it's a function we build ourselves, that we write ourselves, that will also be allowed. So very, very similar. It's almost exactly the same, really, as using the functions in MATLAB. It'll be used in the same way, can be manipulated in the same way, called in the same way. Now what we really have to do is kind of figure out how we're going to do this. What are we going to do to create functions like this? So what we're going to do is we're going to create a very simple function first of all. Let's see, where would this start? Function, okay. So we're going to actually create a function. They go through this long hullabaloo about how you might use a function called a function, but we're actually going to just go ahead and create a function at this point. I'm just trying to figure out where they actually do their first actual building of a function. I think it's, oh yeah, okay, it does start on 208. So at the top of page 208, they actually build their very first function. You don't want to type your function just into the command window. That's not the place to put your function. You actually want to open a new script. So you're going to go up here to new or new script or whatever, and you're going to open up a new script. You could also open up a new function. Either way, you can create a function inside of a script file, or you can create it in a function file. If you open it as a script, it's just going to open up like usual. It just looks like a blank text file, nothing, no big deal. If you open up a new function, however, new function, it will open up with some stuff already put into it. It's actually kind of preloaded the script so that it's ready to have a function written in it. So here we go. We're going to write our first function. This is not something that you necessarily need to save separately for your notes for class today. You can go ahead and write this into your script, write all the stuff we're going to do right now into your script, but it's helpful to open up the function right now so you don't have to type all this, because I'm just going to fill in blanks instead of typing a bunch of stuff in. But you can see at the top of 208, there's something very similar at the top of 208. There's this thing called function output, and that's essentially the name of the function. And so I'm just going to add to this output. So this first line, this first stuff in this first line is actually the name of our function. So I'm calling my function output essentially. And I'm going to erase these two output arguments here that are in square brackets because we're not going to use those yet. That's not something we're going to do. But then it's going to be equal to something, and this is actually the call sign of the function, or so this thing right here is what's coming out of the function. This is actually how you call it, and it's actually what it's going to be named in the end as well. So this is the name of the function. Poly is the name of it, and then it has these parentheses after it that tell us what is going to be the variable that we're going to use in this function, the input variable, in other words. And we're just going to use X as our input variable. The input variable is the thing that we're going to do all of our math with inside of the function. Okay. What does all this mean? I mean, that gets a little bit confusing. The first thing in the blue, MATLAB recognizes as something that it knows what to do with because it highlights it in blue. And that means that MATLAB knows that you're starting a function. That's all that does. When I write function at the top of this file, MATLAB immediately says, okay, he's going to be starting to write a function. And then the next thing that I write in there, it's going to know that the thing that it's going to spit out of this function, it's going to call it output. So whatever I call output in this function is the thing that this function spits out. Okay. So I'm going to write output down here later eventually, and you'll see what that means. But then the output is always going to equal this function name. So the name of this function is going to be poly, and then it's going to have a variable in it called X. That's all that this line means. And that's a little bit confusing because the syntax is not kind of self-explanatory, but that's the idea. Now, if I save this right now, I go up here and I hit save, it's going to ask me if I want to save it with the name poly because that's what it recognized as the name. I'm going to go ahead and save it like that. And you'll look over in your current folder, it has now saved a function file as poly.m. Okay. Then you can go ahead and put in some description of this here. You can say, and up on page 208, it says this function calculates the value of the third order polynomial. So I might just write that. This function calculates the value of a third order polynomial, right? Just like that. And you could do some more explanation. Sometimes people like to tell who wrote this function. They like to take credit for their work. So I said Jared was here or something like that, right? And then in these places where they have output argument equals input argument, this is where we're going to actually tell the computer what to do with the stuff that gets plugged in. We start off in this particular case by saying the output of this function is going to be equal to this thing that I want to do. And in this particular case, we have output equals 3 times x dot cubed. So I'm doing 3 times x dot cubed. And then I'm going to do plus 5 times x dot squared minus 2 times x plus 1. Okay, so what does that line mean? That line says that we're going to name a thing called output, and output is going to be equal to 3 times whatever we plug into this function. Whatever we plug into this, we're going to take 3 times that thing cubed, plus 5 times that thing squared, minus 2 times that thing minus or plus 1. So it's going to plug whatever we plug into for x, it's going to plug it into this equation and call it the output. And this function knows that the output is the thing that it spits out, because that's what we put right here. This is what the function spits out. This is the name of the function. This is the thing that the people plug into the function. At the end of the function, when I'm done creating this function, I need to end the function. I need to put the word end there. And it tells MATLAB that it's done dealing with this function. And then I go ahead and save it. Now I can go down to my command window and I can actually use this function. This function is called poly, and it's expecting some kind of input. So plug in 1, for example, and hit return. It gives you an output of 7. And if you go back into here and you plug in 1 to everything in this polynomial, you'll find that you get 3 plus 5 minus 2 plus 1, which is 7. You could also plug in poly of 198, and it will calculate the value of that polynomial for x equals 198. You can also plug in an array of numbers. You could plug in the array. Let's say that x equals 23, 45, 6, 3, 12, and 90. X equals that now, and now I'm going to just say poly of x. And it does the value of that polynomial for every number that I put into that array individually. You could put in a matrix of numbers, a rectangular matrix of numbers. You can do all kinds of things. So we have essentially created a function that calculates the value of a particular polynomial for whatever number we plug in to the function. Very simple function, but illustrative. In the practice exercises here, they say create some MATLAB functions for these different mathematical functions, for like x squared, e to the 1 over x, sine of x squared. And you would essentially just replace in this function the equation that's in those practice exercises. The right side of the equation would go in here, and the left side can stay as output. Your y of x is essentially your output, right? Or your f of x, or whatever it is your output. They do an example in example 6.1 where we're converting degrees and radians, or calculating ASTM grain size. These kinds of functions are ideal for doing calculations where you want, let's say that you want to calculate, one of my favorite things to calculate is the hang time of an athlete, right? The hang time of an athlete is how long they're in the air when they jump. Because it always surprises people how short that and how small that number is, how short that time is. Anybody want to guess how long an elite athlete spends in the air, how much time they spend in the air? The best jumpers in the world are always high jumpers. High jumpers can jump, they can clear their entire body over 8 feet usually. And guess how long they're in the air? Anybody? Anybody want to say, I'll give you choices here. We'll say 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. Anybody think 1 second is the answer? We have one person. Anybody think 2 seconds is the answer? Another person, another 3 people. 3 seconds? Anybody for 4 seconds? Nobody for 5 seconds? You're all pretty close. A person that's in the air for 3 seconds is beyond elite. That's well beyond elite. In fact, I don't think there's ever been an NBA player who's had a 2 second flight time, air time. I think the best one of all time was, what was that short guy who could dunk back in the 80s? Not Bogues, but the other guy that was pretty short. I can't remember. But anyway, he had a hang time that was almost 2 seconds. Jordan had a hang time that was like 1.7, 1.8, and he was one of the best jumpers who ever played the game. Who's the guy that jumped over the 7-footer in Spain in the Olympics? Can't remember his name either. Yeah, Vince Carter. Incredible vertical, like 1.8 seconds, right? High jumpers, 2 seconds, right? High jumpers are in the air for 2 seconds max at best. Surprisingly enough, I mean, the NBA has set all kinds of records for hang time, but surprisingly enough, the best records in hang time are actually set by shorter athletes who have just incredible jumping abilities. Because in the NBA, the average height is around 6'5", they don't really have to jump so high to reach their goals. To dunk the ball, for example, most players don't have to jump that high. But for example, in weightlifting, you have these really short people that have incredibly fast twitch muscles. They're able to lift something like 3 times their weight to above their head in less than a half a second, or a tenth of a second even. So their fast twitch muscles allow them to jump very high as well. They use those same muscles. And almost everybody on the Olympic weightlifting team in the United States could dunk a basketball, men and women, and they were all under 5'6". 5'6" person who's weighing like 250 pounds could jump and dunk a basketball without running. Just jump straight up and dunk it because of their incredible fast twitch muscles. And their hang times are really quite long, right around 2 seconds again. So it's kind of interesting. That actually plays into my real field of study, which is physics, because the science and math and computers are playing such a huge role in sports right now that it's changing how things are done and how things are taught and how people are trained. Jumping, for example, it used to be thought for a long time that jumping was all about strength and about maybe agility. If you had this stretching routine or something, you could jump higher, or some other thing, strengthen your legs, strengthen your arms, strengthen your core, all this stuff. And it actually has nothing to do with any of that. It has to do with one thing, and that's speed. The faster you leave the ground, the higher you're going to go, no matter what. It doesn't matter what your weight is. It doesn't matter what your height is. It doesn't matter what your strength is. It matters how fast you're moving when you go up. How fast you're moving upward will determine how high you go every time. And that's the physics of it. And so jumping is completely, the training of jumpers has completely changed. No longer is jump training including things like squat lifting, except in the fact that if you can squat really fast, then you can jump really fast. So instead of squatting heavy weights, if you want to jump high, you should squat lightweight very quickly. Try to jump essentially with weights. And instead of pushing that machine that you push your legs with, instead of doing big heavy weights with your legs like that, you shouldn't. You should do lighter weight more quickly, because what you're trying to do is speed up your muscles, not strengthen your muscles. And that's the end of it. I mean, you look at like Kobe Bryant, an incredible jumper, but he wasn't hugely ripped. I mean, he had great muscle definition, but he didn't have huge body muscles. He was just really fast, and so he could jump really high. Another great example of that's even more poignant, that actually is a big man in the game right now. JaVale McGee is skinny and really, really tall, but for his height, he has incredible vertical. The guy can touch over 12 feet, which is insane, even for a guy that's 7 feet tall. And so he can touch the top of the backboard essentially. So it's all about speed, and the science and the math and all the computers that they've used to change training has made a big difference. So anyway, all right. So let's go. That's a little bit of a tangent there, wasn't it? So moving on to now. It's really important on page 213. They actually make a little aside here to talk about commenting your programs, commenting your functions. It's very important actually to write inside the function using comment lines what the function does, just so that you avoid confusion. So make sure that you take advantage of that. Now, functions with multiple inputs and multiple outputs. Let's go on to do something like this. There are many functions that are built into MATLAB that have multiple inputs. For example, the remainder function. I don't know if you remember this one. We did learn about this one before, but the remainder function takes two inputs and essentially it divides the first one by the second one, and then it tells you the remainder. So if you put in remainder 5, 3, it takes 5 divided by 3 and gives you the remainder, which happens to be 2, right? And so there's two inputs, one output, and you can totally do that. There's no problem with that. How does that change? Well, it changes as you're up here in your function. So if I go up here to my function thing again, and I change some things a little bit, we're in the middle of page 214, about halfway down to, just right there after similarly on 214. We're going to create a new function. It's going to be output equals now G. We're just going to call it G instead of poly. So I'm just going to alter this one here. And instead of X all by itself in here as one of the inputs, we're going to name another input, Y, right? And the reason that you give them names in this is not so that you don't have to plug in something called X into this function. The reason we give them names in this is because this syntax here tells MATLAB whatever the thing is that first gets entered into this function, we're gonna put into X down here. The second thing that gets entered into this function will go into Y down here when we make our calculation. The calculation is going to change, and it's also going to change, what we write here. It says X and Y, this function multiplies this function multiplies X and Y, and that's fine. So I've decided, and then also you might want to say like what they say here. They say, X and Y must have same dimensions, so you want to make sure that they're the same kind of matrix or whatever. And then we just go down here and we're going to now, we're going to change this to, we're going to actually put a new line in here. We're going to say A equals X times Y, and it's going to be X dot times, because it could be matrices as well. X dot times, where's my times? There, Y. We're going to go ahead and put a suppression here. We're going to suppress the output so it doesn't print to the screen, because sometimes it can do that. And then the output, we're going to just set equal to A. We're going to say output equals A in this case. We could have done this differently. We don't have to have both of these lines in here. We could have just said function A equals and gotten rid of this line entirely. And then A would be the output, and that's fine. You don't have to call the output. You can call it whatever you want. They just decided to do it that way. Whatever, it's up to you. There are a million different ways to do things, just like always. But this function now is going to be changed, and if I save it here, it's not going to rename it. So if you change a function's name up here, you better change the function's name elsewhere. Let's see if poly will actually. This used to actually bring up an error. Let's see if it still does. If I now call poly, and it has two inputs now apparently. So if I do 1, 2, then it should multiply those together and give me 2, which it does. But I might be able to even call G now. I'm not sure if it will do this, but let's see if it does. 1, 2. So yeah, so now I've named this function G inside the function G, but outside of it on the file, I've called it poly. So now it doesn't have the same name inside and out, which can be confusing, right? So if I want to save this as the function G, or maybe I want to change it to multiplier or something like this. I want to call it something else, and I want to save it as that function, then I need to go up here to save as and save it as multiplier instead of G. And then it'll give me a new function over here called multiplier, and I can come down here and use that multiplier, and I can do multiplier of 7 and 8. Yep, that's what I meant. Must have spelled it wrong. Oh, I spelt it wrong when I saved it, actually. It's not multiplier, it's multiplier without the I in it. Whoops. And make sure you spell your function names right. And of course, you can also plug in arrays of numbers as long as the arrays have the same dimensions. So if I create an array A equals 1, 4, 5, 7, 43, and I create an array B, something like that, 2 1x5 arrays, and then I do multiplier of A comma B, then it can do that, same size arrays. All right. And of course, you can keep doing this ad nauseum. There are many, many different ways, many different kinds of functions. I mean, there's an infinite number of functions you can build, essentially. Of course, you don't have the memory to build that infinite number of functions, but whatever. Let's do this next one. It's going to be the distance velocity calculation. So it's essentially we're going to calculate. We're going to put in a time. Let's see. This is going to calculate the acceleration, the velocity, and the distance of something. I don't know what. I can't decide what. But you're going to plug in one number, which is the time, and it'll tell you the distance, the acceleration, the velocity, and the distance from that. Whatever. So we essentially have one input and 3 outputs, which is also possible. In this case, you need to, since you have multiple outputs, you can't just have a single output variable here. You have to have multiple output variables. So you're going to have an array of output variables. So you're going to have to put square brackets in. When you put in those square brackets, then you can name your output variables. They're calling them distance, velocity, and acceleration, and that's fine. That works. And then over here, they're calling this one motion. They're calling this function motion, and the input variable is going to be t for time. It's good to use variables up here that make sense, even though it doesn't matter what you use up here. You can use anything you want. It doesn't matter, but it makes sense to use ones that go along with what you're doing. And then I'm going to go ahead and save this right now before I forget. I'm going to save it as. And I'm going to save it as motion so I know what to call motion.m. It's going to save another file over here in my current folder, another M file or function file here. The function files will always have this little f of x on them, which means that they've already kind of pre-populated. They've got this pre-populated syntax in here. But now we need to set up our equation and tell us that this is something to do with motion. Whatever it is. Function calculates distance, velocity, and acceleration of a car for a given value of t. For some reason, we know how to do this. But anyway, we're going to now calculate each of these outputs with a different equation. Acceleration is going to be 0.5 times t, right? And they do a dot times there, even though it's actually not necessary. But then they're going to go ahead and suppress the output, and then they're going to do a velocity one. Velocity is going to equal t squared over 4. So we're going to do t dot squared divided by 4. Suppress that output, and the distance now. Distance is going to equal t dot cubed over 12. Suppress that output. And then we're going to go ahead and save that again. You have to save your functions before you try to run them. Otherwise, it won't know what they are or what they're supposed to be. And then we're going to go ahead and try to do this. We're going to do motion. Let's do t equals 4, for example, right? The problem here is that it's only giving us one output. And the reason for that is because we haven't given it a place to put all 3 of these outputs. Answer can only accept one output. However, if we create an array of numbers that this function can put three things into, then it will spit all three of them out. The only thing that it spat out, it looks like, is the last one. It spat out distance maybe, or say 4 cubed is what is 4 cubed? 64, right? 4 cubed is 64, divided by 12 is actually a little bit more than 10. 64 divided by 12, what is that? Is that 5? Yeah, I think that's 5. 5.3, yeah. So they actually only spit out the last one. It didn't spit out the first two. So if we want to spit out all three, we have to create an array that has 3 spots available, 3 things that we can assign these things to. You can call them whatever you want. You can call them A, comma, B, comma, C, or A space B, C, and set this equal to motion 4. Then it assigns them. In the book, they actually say, well, why don't you just call them distance, velocity, acceleration? We can do that too. We can do distance, velocity, and you can put commas between them if you want, acceleration. And then set that equal to the motion at 4. And it will put those in there like that. So you can also do the same thing and suppress the output so that it just saves those things over here in your workspace. It saves the acceleration, the distance, and the velocity over here. So we've now learned how to do a very simple one-to-one function where you plug in one number, you get out one number. We've learned the basic syntax of functions doing that. Then we've built a function where you plug in multiple numbers and get out one number, and you plug in one number, and get out multiple numbers, right? Multiple things. So, and of course, this one can also accept matrix of times. You can do many different times in a matrix and calculate all kinds of distances, velocities and accelerations. So if you wanted to, so let's say we wanted to plot this distance, this velocity, and this acceleration. We could do that. We could set up a matrix of times that goes from 0 in steps of 0.01 to 30 seconds or something like that. So from 0 to 30. That's our time now. And then we can go ahead and do the motion over time. And it calculates a whole bunch of things. Now our acceleration is a 1 by 3,001 double. Distance is a 1 by 3,001 double. And velocity is a 1 by 3,001 double. In other words, we got a lot of information now. And now I can actually plot the time versus one of these things. So I can do distance and time. If I plot distance and time, it gives me this thing, which I'm going to dock. So it gives me this graph here for this is what my distance looks like. At 0, I'm at 0 at 500. That's not 500. That's not proper. Let's see. Oh, so this is distance. This is time. Let's do it the other way. Sorry. I want to do time versus distance, not distance versus time. Let's do time on the x-axis, distance on this axis. There we go. That makes more sense. So now after 5 seconds, I haven't gone very far, but I have gone somewhere. If you put your cursor on there at 5 seconds, it'll tell you how far you've gone somewhere. I can get it to show up. But as you're going further along here, you can see that you're going further and further for every second that you move. Between 25 and 30 seconds, I'm moving a lot further than I was between 0 and 5 seconds. And if I want to plot time versus velocity and see how my speed is changing during that time, it also has this kind of curve. But I could also plot my acceleration, and you'll see that the acceleration curve looks quite a bit different. It's a straight line. That means it's a constantly increasing acceleration. Something that constantly increases acceleration like this would be like a rocket going into space. This is what the curve, these are what the curves look like for a rocket going into space. And it kind of makes sense. If we do this, if you're looking at a rocket takeoff from Cape Kennedy or whatever, this is actually what it looks like. When it first starts to take off, it hardly moves at all, right? it's just like moving a meter and then 10 meters, and it's moving really slowly when it first starts taking off. But then after just a few seconds, it really starts to get going. After 10, 15 seconds, this thing is just moving. And 20, and the reason that rockets do this is because they have this rocket stuff coming out, the rocket, exhaust coming out the back. And that gives this constant acceleration of this rocket, however, a constant force on this rocket. However, the longer the rocket burns, the less mass the rocket has. So the longer the rocket burns, it has the same amount of force, but less mass. So it goes faster and faster and faster and faster. And also eventually it gets up into the atmosphere where it's thin and it has less resistance. So it starts to go faster and faster and faster. So this is a very good plot for the way a rocket behaves. That's what its distance plot looks like. This is what its velocity plot looks like. And its acceleration is it's constantly increasing its acceleration in a linear manner. So that's not a bad way of plotting those things. Oh, they actually do that, but they do it in steps of 10. I did a lot more steps than they did. Anyway, whatever. So there we go. Here's a function with no input. This starts on page 218. I'm going to go ahead and clear things out really quick. And let's. Okay. So we're going to create a new function. I'm going to go ahead and close some of these that I've got up here. We're going to open a new function. And in this function, I'm going to have a no input. I'm going to create no input by creating an empty array. An empty array is just a square bracket, open, close, square brackets, nothing in between. You can put a space in between to mean the same thing. And some people do that just to make sure that they know that's an empty function, but that doesn't matter. And then I'm going to call this particular function star. And the function's not going to have any output either, at least not a numerical output. I'm going to call this function star. And so the output is also going to be empty. Now, I believe you can leave the parentheses off entirely and just have it equal star. You don't have to necessarily have it equal to star empty parentheses, but I'm going to leave them empty anyway, just because that's what they're doing. And this, I'm going to write in my thing here, this thing makes a star. 5-pointed. 5-pointed star. Okay. And then I'm going to write the code. And the code is as follows. This code is made for the polar plot. Remember when we did the polar plot where it's in R and theta instead of an X and Y? This uses that polar plot, and everything is written in that polar plot kind of world. I'm sorry? For this? Makes a star, 5-pointed star. That's all I did. That's just an explanation of what it does. Makes a star 5-pointed. Makes a 5-pointed star. How's that? This is not English class. I don't really have to speak proper English, do I? I suppose I should. Okay. So down here in our code for this function, we're going to start off with this definition of, this definition of theta. We're going to create this vector theta, and it's going to start at pi over 2. And it's going to take these steps that are going to be 0.8 pi, 0.8 times pi. And then we're going to go all the way to 4.8 times pi. Now, what does this mean? Okay, so this is creating an array of numbers. I'm actually going to just take this right here and I'm going to grab it and I'm going to paste it down into my command window. I'm going to copy it and paste it down here and see what it does. I'm going to open this up and this is what I get. Maybe, there we go. This is what I get. The first number is pi over 2, 1.57. If you multiply it by 2, you get 3.14. The next one is this thing plus 0.8 times pi. Well, 0.8 times pi is a little bit less than, it's like between 2.5 and 3 somewhere, right? So if I take this and add like 2.5 to it, I get 4, which is exactly what I would expect because I'm adding this amount to this amount. And then I add that amount again. I add another 2.5 and I get about 6.5. I add another about 2.5 and I get about 9. I add another 2.5, I get about 11.5. I add another 2.5 and I get 14-ish, right? And I keep doing that until I reach 4.8 times pi, which is actually, 4.8 is about 5, pi is about 3, so it should be about 15. So this is about the end of it, right? That takes us to the end of this. So that's all it's done is create these numbers that are evenly spaced between pi over 2 and 4.8 times pi. Okay, great. But notice how many points there are. There are 6 points, and each one of these is an angle. So these are 6 angles, essentially. 6 turns, you could think of it as. Or now 6 rotations. You could think of it as. Okay, so now the next line that I'm going to put into this thing, I'm going to close this out. The next line of this code looks like this. R equals ones. Remember, ones makes an array filled with ones. And we want this thing to be 1, 6. Okay, well, what does that do for me? Well, let's put that into our thing down here. R equals ones, 1, 6. What does that do? Look, it makes an array 1, 1, 1, 1, 1. And there are 6 of them. 6 angles, 6 ones. Okay, well, what does that do? Well, the last thing that we're going to do is we're going to make a polar plot. Polar plot, right, is polar. And we're going to do theta, comma, r. We're going to save this. It's wanting to save it as star. I'm going to go ahead and save it like that. And then I'm going to run it. And lo and behold, it makes a 5-pointed star. How did it do this, though? How did it do this? Well, let's actually do polar of something much less let's do polar 0, 0. There we go. Polar 0, 0 gave us 1 point. Can you guess where that point is? Okay, so you're saying it's the center. Anybody else have a thought where it might be? We have 1 vote for the center. Anybody vote for the center also? We also have another vote for the center. Anybody have another one? Anyone else want to vote separately, differently? Okay, well, I think that's fair. Because remember, with polar plots, we rotate around from the center, right? We rotate around from the center for the first order. So we go however much angle this way. Well, we chose 0. So we went 0 this way, so we're just this. And then we choose a length r, and our r was 0. So we went 0 distance away from the center. And so we're right at the center, right? Exactly. So good, exactly. What happens if we do the numbers that we had before for theta and r? The first number that we had for theta and r before, let me get my drawing tools out so we can draw this. Come on, drawing tools, pop up already. Stupid thing. Give me the drawing tools. There we go. Draw. Okay, I'm gonna make little dots. That'll be a good dot. Okay, so in our other numbers here, our theta, let's say, I'm actually going to print out theta again on this screen. So here's theta. Delete. So here's our R and here's our theta. Now we're going to plot out each of these points separately. Remember, you do theta first and then R. So theta is 1.5708, and that's pi over 2, which is actually right about 90 degrees, right about there. It's actually exactly 90 degrees. So our first point is actually going to be right there. Let's put a point there. There's our first point, right? We went, oh, sorry, we didn't do the 1 yet. We did theta, we did 0. We started 0 angle, we went up pi halves, which is up to here, and then we went R equals 1, which is all the way out to here. This is R equals 1. This circle is R equals 0.5. You can see it labeled there 0.5. This is R equals 1. So our very first point goes right up here, right there. Then we go to the next angle, which is 4.0841. And that one was pi over 2 plus just a little bit less than pi. Pi is 180 degrees. So we're going a little bit less than pi. We go 180 degrees about right here, and we put a dot. And then we do it again. We go about 180 degrees, a little bit less than that, and we put another dot here. Then we go another 180 degrees, a little bit less, and we put another dot here. All right. And then we do it again, and we come around to about here. So those are the 5 points that we've drawn when we do those. And then we do it another 180 degrees, and we go all the way back. We do another just less than 180 degrees, and we go back to this point. It actually takes us right back to this point. That's what we just did. We did 6 points, 1 point, 2 points, 3 points, 4 points, 5 points, 6 points. Remember that MATLAB connects the points. So if this is our first point and our second point is here, it's going to draw a line between those. So it does, because MATLAB does that. It connects, this is our first point, this is our second point. Our third point is here, so it connects those. Our fourth point is here, and it connects that one. Our fifth point is here, so it connects that one. And our last point is up here, so it connects to that one. And that's why it created a star. Now, my star is not as pretty as theirs because my measurements weren't as exact. But that's what we just did. We plotted 6 points, and MATLAB connected the first point to the second point to the third point to the fifth point to the sixth point and created a star by doing that. In your homework, you were asked to make polygons. You figured that out because they kind of showed you how to do it, and you were able to figure that out. This one's different though, because this one, you go all the way around to here, and then you go to here, and then you go back around again to create another point, and around again. When you were doing polynomials or polygons, you just did successive points that were next to each other. These ones, you kind of skip around, you go around the horn, you go around the circle more than once, right? And you're going to be asked to do this for a 6-pointed circle. You're going to be asked, or 6-pointed circle, 6-pointed star. Yeah, make a 6-pointed circle. That'll be easy. Anyway, so you're going to be asked to do a 6-pointed star. In fact, I think they even ask you to build a function where you tell them the user tells you how many points to put on the star, maybe. Or maybe you do that for a polynomial. I can't remember, or a polygon rather. But that's what's happening here in this function. So it just creates that star. All right. Oftentimes when you're building your own functions or your own programs in general, you would like to know how fast things are working in your function. We mentioned this function earlier, this built-in function of MATLAB, but there is a MATLAB function called the tick-tock function. If you put in tick right here, oops, clear this out. If I type in tick right here and press enter and wait, then I press talk, right? It actually tells me how much time elapsed between those two commands. So when I put in tick, MATLAB actually remembers the time on the clock, and then, or it looks at the time on the clock, you could think of it as, and then when I put talk, it looks at it again and calculates the difference in seconds, right? So you can actually put this in your function to see how long the function takes. Let's do it. Let's put it in our function right here. Tick. Talk. And let's put an output. Actually, I think that'll just print to screen. Let's check and see if it does. Let's go ahead and see what happens. So I'm going to go ahead and run the star function again. So right there, it tells me the elapsed time for this function was 0.131163 seconds. So about a little bit more than a tenth of a second, about an eighth of a second. Not bad, right? But the purpose for that is that when you're writing programs, you often are trying to make it run faster. That's one of the big deals in computer programming. You can make it run faster, make it run faster. And so if you have a more complex program, you might put a tick-tock in part of it and then rewrite part of it, like change it somehow that you, in a way that you think it will run faster. Because there's, so many different ways to write programs. You can write any given program an infinite number of ways. So you try out a couple of different ways and you find out which way is fastest. Usually that's also the most efficient way to do it. Okay? So a very useful function, very useful built-in function in MATLAB to get this, to make your function more efficient, fast, functionable, whatever you want to say. Okay. So let's see here. So now that you've learned how to build some functions here, we need to know how to kind of deal with them sometimes. So we're going to learn some more about how to deal with functions in page 220, section 6.1.5. If you want to know how many input arguments there are in any particular function, you can ask MATLAB and it will tell you. This is the function. It's nargin, number of arguments in, essentially nargin, right? And then inside the parentheses for this, you put the name of the function in quotes. So if we put the name of the function poly in quotes, for example, it will tell me that there are two input arguments, two things that you have to type into poly function. If I put star instead in here, it says 0 because it didn't accept any input arguments. You just had to type star and it did it, right? If I type in, I can also type in one of the known functions or one of the built-in functions in MATLAB, like the sign function, and it says it accepts one input argument, right? So any function, whether it's something built into MATLAB or whether, for example, you could do plot. It says -1. Why does it say -1? Right here, it says on the about 2/3 to 3/4 way down, it says the surf function is an example of a function with a variable number of inputs. As we've already learned, plot, you can put in one argument, you can put in two arguments, you can put in, there's like 50 different things you can put in there because you can change the title of it, you can change the dot size, the dot color, the line thickness. You can change all kinds of things, and all of those are called arguments within plot. So you can either put in 1 or 5 or 7, and so it gives you this -1. You just have to look it up, use the help command to look it up if it gives you a -1. But if there's a definite number of arguments, it will tell you exactly how many. Then there's also number arguments out, so you can do narg out, right? Number of arguments out of a particular function. If you want to do the star function again, for example, got to put quotes around it because it's a name, right? And it says there's no arguments out for star. And you say, well, wait a second, it gives us a graph. But arguments in and out are considered to be numbers, matrices, that kind of thing. So it's not a graph. A graph is not considered an output argument. It is an output of the function, but it is not an output argument of the function. Okay, let's see. Let's do this function here. They've got this. This is a new star function. Star1, they're going to call it. I know you guys got to go for basketball, so go ahead. Or you probably don't, because. All right, so let's do a new one here. Let's do a new function. I don't want to type in everything. I just want to fill in the lines. Okay, so we're going to do a new function. This is the one in the middle of page 221. So we're going to say function, and we're going to say that our output is called A. It's just going to be a single output A. And we're going to call this thing star1 to distinguish it from the original one, star. And it will have no inputs, just empty. And we're going to say that we're actually doing the same things that we had in star. So I'm actually just going to go over here to copy it. The theta and the r's are the same, right? I'm just going to copy those over here, paste. But it has one extra line into it. The one extra line, let's see, R1's polar, theta r. Forgot the polar part. Copy. Polar theta r. But it has one last one, and it says if narg out is e. So when you put in an if function, you have to give it some conditions. So we're going to say if narg out is equal to 1, you put a double equal sign to ask a question if it's equal to that. Then we're going to say that A, which is the argument of it was the output argument of this function, is equal to this string of letters. You tell it that you're putting a string of letters by putting a single quote. And we're going to say twinkle, twinkle, little star. Right? Just like that. And then you close it with a single quote. So this function does have an output. It has one output, and we're asking if the number of arguments out is equal to 1, which it is because we defined it that way. Then you type this. So it's going to type this on the screen. Did you have a question? Yeah. No. So I'm going to go ahead and save that function as star1, and I'm going to go ahead and run star1 here. Star1 creates the star. Oh, let's see. What did we do here? If narg out equals 1, did I do something wrong? Equal to 1. Oh.
I think you maybe need to put parentheses. Star1 and then parentheses.
No, so I actually know what this is going to do now. So it's not going to type that out unless I ask for the n argument out. So that's what we're going to do here. We're going to do narg out of star, right? Star1. So now if we ask for the n argument of star1, if I ask for this, ask for what this is, right there, right? And then call the function. And then we're going to set this equal to what this is equal to. What is star1 equal to? And then it'll give us twinkle, twinkle, little star. I didn't suppress it up here, so it printed it twice. So anyway, That's just kind of a goofy little thing to show about it, but we'll have much better ways of printing things to the screen before too long here. It's kind of an awkward way to do it. All right, so that takes us kind of to the end of the introduction of these user-defined functions.
Can you go a little bit up again, right?
Where?
It's with the, so I wrote the function A, but then.
This function here?
Start.
Oh. So this right here?
I wrote the function A, just like in the command window. So now.
Oh, in the command window. Oh, so down here, I see what you're saying. Yeah, so right here from star one, when I first put in star one, and then I asked for the number of arguments of star one, it gave me an answer of 1. And then I set x, the variable, I'm creating a variable x and setting it equal to whatever star one is. So it turns out that star one has this output value of A, twinkle, twinkle, little star. And so it prints that to the screen, right? Now that is the output of it, but I suppressed the output I suppressed the output down here, and so it didn't know what to do. So it didn't print it to the screen. But when I set it equal to X and asked for X, then it did print it to the screen. If that makes any sense at all. It's like I said, it's an awkward way of doing things, but just to demonstrate what the function does. The function sets this output variable A equal to whatever the result is inside of your function. And down here we set A equal to twinkle, twinkle, little star. So the function created the star like it was supposed to over here, but then it suppressed the output of the A because we put this thing on here. Later on, you can see that MATLAB knows what it should have been. Kind of goofy. Goofy and awkward, but just to, I guess, demonstrate where those things are being kept. And that actually leads us into the next part, but I think I want to take a short little break at this point where, let's see, we have toolbox functions, anonymous function handles subfunctions. Accessing function code. Okay, let's go ahead and finish up 6.1 before we take a break, because then we'll be ready to just crank out the rest of the sections. This chapter, almost the entire chapter is 6.1. It's like 3/4 of the chapter, and then 6.2, 3, 4, 5 are like all a half a page each or something. Not to mean that they're not important. They are important, but this is the main learning section. The rest of them are different applications of this idea. So whenever you're building functions in programming, and this goes for all programming languages across the board, you're often creating these variables inside the function that are not used outside the function. Like right in here, we created this thing called R. We created this thing called theta. We created this thing called A, but these things are only really used inside of here. Out here, if I type in A right here and ask it what it is, it doesn't know what A is. Even though right up here, it told me what A is from the function, MATLAB didn't remember that, right? However, if I type in X, MATLAB does know that because I defined X out here in the command window. So it knows what X is, but it doesn't know what A is. It doesn't know, it also doesn't know, well, that actually does know what R is over here because I put it over here. But if I clear out my window over here and I run *1 again, right? So I've run *1, it's created the star here, but it doesn't know what R is. If I type R right now and hit return, it has no idea what R is, even though it used it up here. It doesn't know what theta is. It just has no clue. The reason is because these variables inside of here are what we call local variables. They're variables that only work inside this function. They're only defined inside this function. And once this function is done running, MATLAB forgets them and just erases them, doesn't mess with them. It doesn't save them to our workspace. It doesn't remember them all. Local functions only work within the function that they're, or local variables rather. Local variables are only variables recognized within the function that they're created in. However, you can create a global variable that is recognized everywhere in MATLAB, saved in your workspace, and can be used in multiple functions, which is very useful often. Anything that you type into the command window as a variable, if I type in x equals 5 right here, that is now a global variable in MATLAB. But you can define global variables from within functions. I can create a variable up here and make it a global variable so that MATLAB remembers it out here and puts it in the workspace. And the reason for doing that is so this function maybe creates a variable, puts it out here in the workspace so MATLAB can use it, and then another function can use that variable. So one variable can create one function can create a variable, and another function can use that same variable. So you can pass information back and forth between functions. One function can do one thing to this number, another function can take that answer and do something else with it, and so on and so forth. So it's kind of like trading information back and forth, right? So anyway, that's the difference between local and global variables. Now, how do we actually define a global variable? You know, how do we make this happen? So if we go to page 223, we're creating a function that's calculating the distance following object travels due to gravity. Okay, whatever, sounds good. So let's go ahead and open a new function, and we're going to call this function result equals distance, and it's going to be, there's going to be one local variable t. That's our local variable t that we're going to be using. And then down here, we're going to have our equation that defines what we're trying to do. And that equation is going to be result equals 1/2, so 1 divided by 2, and then we're going to times g times t dot squared. The problem is that g is a constant here. G is a particular number, and it's always the same number when you're on Earth. So we're going to actually create a global variable by saying global g. All right. And then we're going to save this. Save it as whatever it's saving as, distance, I guess. Now, if we come down here and we say distance, let's say in 5 seconds, how far are you going to fall? Well, there's a problem. Error in distance line 6. So we go to distance, line 6. Oops, that's not good. Let's erase that and save again. We're going to get a different error next time anyway. It's not the error we were looking for. Let's try it again. Distance 5. So here's the problem. It gives us no answer. No answer whatsoever. And the reason is because it had no way to calculate it. This global variable g was never defined. Now I could go ahead and type in what g is in here, or I could define g inside the function if I wanted to, or I can define it out here. Either way. Because I've made it a global variable, I can define it wherever I want to. So let's try and let's define it in here. Let's say that g equals 9.8. Right? So I define it in there, I save it, and then I run this again. Distance 5. Oh, didn't like that either. Apparently I can't do it either. Probably. You're probably right. Let's try that again. Yeah, there we go. So now it's giving us an answer, but also we should be able to see what G is out here. Let's see if we can. Nope, we can't see it here. We should be able to use it in another function though. It actually didn't save it to our workspace, so that must be different. But if we have another function, we should be able to use it. I don't know, see if we can use it in another function here. I'm going to put G into this function now. I'm going to call this G times this. G times pi. I think I have to declare global G here as well, though. That's just going to make a mess of that graph. Let's not do that. Let's go back to this and see if we can define G outside of here. So let's run distance again. Let's save this really quick. And when we run this, that shouldn't work again, right? But, oh, dang it. Oh, yeah, it's actually saved G. So it actually is still running it to global G. I have to clear that. So the global G variable has been saved apparently. And then if I clear it and then run distance, hopefully it shouldn't remember that. Let's see, what did it do? Oh, it's still remembering G. Why is it? The global variable, I can't remember how to clear a global variable all of a sudden. Let's see, do they tell us how to clear a global variable? I don't remember. Stylistically, see also clear vars, yeah. Vars. Still hasn't cleared it. Come on, we want to go to clear. Here we go, clear global. Yeah. So let's do that. Clear global. Now let's try it. Here we go. Ah, it still hasn't done it. Clear X if clear. If X is global, clear X removes X from the current works. Use it. Oh, there we go. I know there's a way to do this. I just can't remember what it is. Function clear global removes global variables that match regular expression patterns. To clear specific global variables, the global option must come first. Otherwise, all global variables will be cleared. Clear global. Oh, it's in all capitals. Maybe that's the difference. Here, or maybe not all capitals. Should do one or the other. Yeah, there we go. So finally cleared it. But anyway, so what happens when you enter in a global variable apparently is that it's not going to save it in your workspace, but MATLAB will remember it. You've essentially kind of programmed into the MATLAB so that any function that uses this G variable now is this G thing is it's gonna know what that is, and it's gonna be kind of pervasive throughout MATLAB. The upside to that is you do have this option, you have this ability to share this number with a lot of different functions. The downside to it, as you can see, is that you have to remember to clear them. Otherwise, MATLAB remembers that and you're in trouble maybe later on if you don't remember that MATLAB knows that and you call something else G, because a global variable cannot be erased or cleared any other way than by doing that command clear global. You have to make sure that you do it right. So it has its upsides and downsides. Most people will not mess with global variables, just so you know, but sometimes they do. So if you're looking through some code at some point and somebody declares a global variable, the light should go off in your head immediately, and you should say, okay, this thing is going to be available in a lot of different places in this code. A lot of different functions are going to be using it possibly. It might get passed around here and there and whatever. So it's something that I need to keep track of and understand. That's the most important thing about understanding global versus local variables, in my opinion, is that you have to be able to make sure that it's being tracked while you're dealing with the code. You know what it is. Okay, now that is. Did you do it with all lowercase? Because I did it with all lowercase and all caps just to cover my bases. So, yeah. I think it's one or the other. I don't know which one actually worked, but I tried both just to make sure that if it was one or the other. I think it's probably all lowercase. It didn't? Huh. What your MATLAB version is 2018 or what? Yeah. I don't know why it wouldn't clear. I didn't do anything else, did I?
I was having the same problem. You have to delete what g equals to in your function.
So I removed it from my function and cleared it.
Yeah.
Okay. So yeah, I removed. So if you run the function again and declare g as a global variable and then define g, then it definitely will just keep making it a global function. But if you erase g equals in your function, then you don't have it there anymore. And I think that I can define g from here as well. So if I say g equals 9.8, and let's see if this is actually true, and then go to distance 5. No, it's not going to recognize it. I have to declare it out here as a global. So then if I do this out here, I have to actually declare global g out here, I believe. And then start to declare random global phrase. Change to match the global. See, and there's always some kind of warning when you start messing with global variables because it can be really messy. G equals 9.8. So yeah, you can declare it in the command window and use it in the function. Or you can declare it in the function and use it in other functions. But were you able to get it to clear at any point? No. So did you erase it in the function and rerun the function? And then do the clear global? Okay, you must have done something. No, well, I do have it in there, but I erased the definition of g in my function. I kept the global g in my function. I kept the declaration of g as a global variable up there, but also just not going away. So what did you do to finally get it to go?
I did that. Like I followed it out, but global G just like the one.
So you took that out of your function?
No, I put that back.
Put that back in, but then you took out the actual definition of it.
Yeah.
Here, okay. So if you erase the g equals 9.8 from your function and then save it, and then declare global in your command window. Sorry, not declare global, but clear global in your command window. Then it works. And I mean, really, this is a great illustration of why global variables can be kind of touchy, because you can declare them in multiple places, you can use them in multiple places, but that is kind of like a double-edged sword, because then MATLAB starts to get confused, the programming starts to get confused, but it can be useful. What's that?
I didn't understand, like, if we declare G outside of the function,
Uh-huh.
if we want to call the G inside the function, we can do it.
You have to declare it both places if you want to define it outside of the function. So if you want to define G as 9.8 out here, you have to declare it out here and define it out here.
Yeah.
But you also have to declare it in here so that this function knows to look for G out here.
So I cannot do like type in like outside of the function, I cannot type like G equals 9.8, and then in the function, I just call G, variable G.
Yes, so
It's not gonna work.
no.
I need to decide variable, inside the function, I
Yep.
need also to call G equals 9.8.
if it's not gonna be global, then yes. If you're doing a global variable, then you can define it in the command window and use it in the function.
Oh,
And it seems really convenient to do that, and it is in many situations, but there are dangers. It can get messy.
I thought the variable that you define outside the function is basically global.
No. So that's what I'm saying, is that anything that's in the function stays in the function. It's kind of like Las Vegas, right? This is Las Vegas. Everything that's here stays here unless somebody writes about it. And that's when you declare it a global function, right? So unless somebody brings their phone and twitters, right? So that's what this is doing. This is like making it known to the world that this is being used here, and we're going to use it
My
elsewhere.
main question is if we define global outside of the function, so outside of the function, in command window we say global G
Mhm.
and everything, and it equals etc. And in the function we call just G, just variable. We don't define it. It's gonna then recognize that it's gonna work.
You still, inside the function, I believe you still have to tell the function that G is a global variable. The function needs to know that G is a global variable as well. So you name it, you create a global variable, but then you tell the function this is a global variable. I believe that both of those things have to happen. I'm not sure. Let's check. Let's do it. Let's try it. I'm going to erase it from here really quick. I'm going to save this. So right now, this function thinks that G is not a global variable. You can see it's not lit up. Even though outside here, I've declared G as a global variable, I'm pretty sure. No, I didn't. Let's do it again. Yeah, I did right there. I did declare it right there, and it's not been cleared. So MATLAB thinks G is a global variable, but this function doesn't think that. So I have to declare it as a global variable in here in order for the function to realize that. Oops. There we go. So it has to know. And that's kind of the big deal with functions. It's like a program within a program. And it's like it doesn't even know the outside world exists. It just does its little thing and spits it out. And it doesn't care what's going on outside. Inside the program, it can use X and Y and Z and Q and whatever. And those can be completely different things than the X and the Y and Z and Q out here. It doesn't matter. It doesn't care what's going on outside. It just does its work, spits it out, and goes to sleep and waits for the next time that you use it. Right? And that's important because that's very valuable. It's great to have things that don't do anything until you tell them to do it, right? They just sit there and wait for you to put numbers in, and they do the same thing every time. That's great. That's exactly what you want, right? So that is the idea of the different kinds of variables, and they do some other examples here. They're going to generate a sphere, and it's pretty complicated and takes a lot of time. I mean, it's not really difficult to do this. This is at the very end. They're calling accessing function code, but here they're going to show a function that creates a sphere, and you can actually do this. You can actually use this function in MATLAB. It plots a sphere, I think. I don't know what let's do. I think this is actually a built-in function. Yeah. Just sphere graph, and the sphere is a surface and do not return anything. Yeah. So I think we can just do this. Let's try and see what it does. Yep. So this is a built-in function in MATLAB, and it just creates a sphere. It's a radius of 1, this sphere, three-dimensional sphere. It doesn't look like it because it's all scrunched up in one dimension here. These two dimensions are much bigger on the graph than this dimension. But it is just a 1 by 1 by 1 sphere, and if you rotate it around, you can kind of get a feeling for that geometry there. And so what if we want to know what is inside of this sphere? What's inside of this function? Well, we can actually look at it. We use type sphere. And look, that is the code for this function. First, they give you the information about sphere. That's the help function. That's the thing right there. But if, let's see, where does this start? Yeah, starts right there. So first it gives you kind of the basic information about the sphere function. And then down here, it actually gives you all the code that's in this function, including the commentary that's in the code. Simple enough. So that's kind of nice. And you can do that for any function. You can do that for the sine function in MATLAB. You can do it for any function in MATLAB. You can actually figure out what the code is behind it, behind the function. So now let's take a little bit of a break, a few minutes, take a walk, get a drink, go to the bathroom if you need to, whatever. Let's see what time. We'll come back at about 40, about 2:40, and we'll finish up the chapter. Ooh. Okay. Now, we all know how to make functions. We're going to learn some things about organizing functions, creating functions in kind of a shorthand, quick way. We're going to learn about sub-functions, and then we'll pretty much be done. So we're going to go 6.2 through 6.5 now in about 6 pages, 5 pages. So toolboxes of functions. So a toolbox of functions is kind of it's like having a folder or a file box full of functions that you use for a particular reason or that are all related to each other for a certain project or something. So as you're programming in your career or something as an engineer, you may be working on an airplane at some point, a particular airplane like the new fighter jet for the Navy or something. And you might have an entire toolbox of functions just for the guidance package for the missiles, and another one that's just for the radar package for the radar display, and just all these different places. It's a way of organizing functions, really. And you do this using some particular tools. They actually show them here on page 225. You have this set path kind of function, built-in function in MATLAB, and a path tool function. These commands that you can put in, where you're going to figure out, you're going to choose, I guess is the best way to say that. Choose where these files are, all these functions are going to be kept. Excuse me. So it's kind of like a way of organizing your folder, your MATLAB folder, from within MATLAB. And that's useful because you don't necessarily want to write function after function after function and then go in and point and click and drag things into the correct folder. You just want to say in this MATLAB, this one goes with this, and put it right in the function, and you can do that. And that's essentially what they're showing here. There's not really, there's also an add path function. And we've not really created enough functions to do this. I suppose I've got 1, 2, 3, 4 here. I guess maybe we can do it. So I suppose we can do it. Let's see. I'm gonna have to create some folders if we want to do this. I've never actually had enough functions to have to worry about this. But if we go, we can either create the folders within MATLAB from this command window, or we can, let's just go ahead and do that. Let's just do the set path, root. All right, set path. Okay. There we go. No. So let's do path tool. Okay, there we go. So the path tool just brings up this window. This also you can also bring this up by going, by clicking on one of the buttons up here. I can't remember which one it is and I can't find it. Here we go. Here, if you press this set path button up on kind of the upper right section, then that will change this, that will open up this window as well. So from this window, you can add folders. You can add a folder with subfolders. You can move folders up and down, move things, around, and you can remove folders. So it's just a quick way to do a bunch of stuff. This is where I'm at right now, is inside of this folder here. And let's see, if I want to add a folder here, I can. And where do I add it? That's a weird place to take me. Let's go to here, go to here. Oh, that's right, that's place. So I'm going to say, let's do a new folder. And what is today? We'll just call it Wednesday. This is my Wednesday folder. I'm going to create that. And then I can start to, so I can start to put things into this Wednesday folder. It's now over here in my current folder path thing here on this, and I can go ahead and save this and close it and be done. But now I've got this new folder over here where I can start to save functions, and I can drag them into there, or I can actually put them in there. Now, putting them in there requires I know it can be done, but they're not telling us how it's done here. I don't remember the code for it, but you can actually write it directly into the code. And it's actually a fairly simple command. I just can't remember what it is. And I think we learn it in chapter maybe the next chapter, maybe 7, but it might be later on too. No, I think it is in chapter 7 possibly. But you can actually write into the code, I want this to go here, and it will just send it there. It will save it there. And it's not very difficult, but we'll learn it here in the next chapter. So anyway, that's what they mean when they talk about a toolbox of functions, and it's called different things in different languages. We call it a toolbox in MATLAB. Some other languages call it toolbox. Some other languages call it a folder or a file or whatever. There's all kinds of things that people call things in coding, but that's just one way to do it, one way to call it. All right, this next one is kind of important, and this is the use of anonymous functions and function handles. All right, so an anonymous function is kind of like a shorthand function. It's like a really quick function that you can build right into some code or right in your command window really quick, and then you can use it really quick. You can use it over and over again really quick. So a quick example of this is on the top of page 227, where we define an anonymous function as ln. We call this function ln, and it knows that it's an anonymous function if we set this equal to the @ sign. Okay. That right there tells MATLAB that, oh, they're defining a really quick function, this anonymous function. Usually anonymous functions are really short. But the first thing we got to do is tell it what our independent variable or what our kind of local variable is going to be for this function. So we're defining a local variable for this function, x, and the function comes next. You put a space and then you put the function. We want log x, the function log x, to be equal to ln now, and that's fine. So we're not doing anything really fancy here. We're actually just we're giving this function log that MATLAB already has a shorter name or a different name. But you can also do other things in here. You could say log x times the sine of x squared minus 4x or something like this. You could make it much more complicated if you want to. And then all of a sudden you have this quick function that you've created that's a function of x. Now the next time
So now that I've done this, oops, I forgot something. What did I forget?
Next before that, you didn't put the spot.
What did I do? Sorry.
So you have a log x times sinus, and then in parentheses, you have x squared minus 4x.
Oh,
So if
yes.
want,
Thank
maybe
you.
4 times it.
I wasn't reading the, yes. I wasn't reading the error. Thank you. I thought it was an error in the way that I entered the anonymous function. Okay, so once you've entered your anonymous function, then it does two things. If you leave it open like this without a semicolon here, then it tells you tells you the information about this function. It has a function handle, which is ln. ln is now the new call sign for this function. And then it also saves it over here as with this little cube, which tells you that it's an anonymous function. And now I can use the ln function and plug a number into it or an array into it or something. So the ln of 9 now is going to plug 9 into this function, log of x sine, it's going to be log of 9 times sine of 9 squared minus 4 times 9. And it will calculate it really quick. So it gives you a really quick way of making functions. So these are called anonymous functions, and the function handle is the name that you give it. A lot of times people will actually call them a handle. So the one at the bottom, they call it a distance handle, right? And that just tells you that this is an anonymous function with this function. But you can do all kinds of things with that. You can actually put anonymous functions within functions. You can build a function up here in one of these function files and put anonymous functions in there, and that works too. But it's a real quick way to build something that you say, for example, you need to do the same calculation many, many times. You don't want to just keep copying and pasting it or keep, going up and down and changing things. Just create an anonymous function real quick and then just use it over and over. Useful little tool. Right. Oh, and if you want to plot an anonymous function, you can do that. So you can plot an anonymous function like this. We're in about a third of the way down to page 228. You use a different plot command. It's the fplot. So if you want to plot a function, you have to use the fplot, and then you have to tell it the handle. So we're going to use the handle ln, and then you have to give it a range of numbers to plug into ln, or a number to plug into ln, or an array of numbers, matrix of numbers. So in this particular case, we're going to plug in this array 0.1 to 10. So this is giving it this range of numbers to plug in. It didn't like what I did. Function behaves unexpectedly on array inputs. So it's not, this is not ideal what I did, but you can see that it actually worked. It's kind of a cool little function, actually, I think. Plotted it in a 3D array because I had a 3D array open, or a 3D plot because I had a 3D plot open. But anyway, you can plot these functions as well. You just have to tell it where to plot it from and where to plot it to. Now this actually gives us this actually gives us now a way of plotting other functions in MATLAB. Because did we use fplot in the last chapter? I can't remember. So I think that you can actually use fplot to plot like the sine, excuse me, the sine function. I don't think it has to be an anonymous function. Let's check to see if that's true. So if I want to do the sine between 0 and 2 pi, for example, 2 times pi, I believe that it will sine, let's see. No, apparently it won't do that. So it does have to be an anonymous function. So to do that, if we wanted to do that, then what we would do is we would define a new sine function. We call it sine equals add x sine of x, right? To get around that. And then we do f plot sine with an e now, 0 to 2 pi, and we can plot the sine function. And MATLAB actually just creates a plot with a certain number of points in it that, to make a nice smooth plot. So that's 6.4. Now we're on 6.5 all of a sudden, which is the last section, I think. Yep. And these are sub-functions, right? So sub-functions are essentially functions written within a function file. Sub-functions are not written exactly the same way, but they are written in a similar way to functions. I'm not going to write one out just because it's a pain in the butt to do it, but if you look on page 229 in the book, you can see a set of 3 sub-functions written into, well, maybe there's an example here that's not so mysterious and weird. Not a great one either. It's a calculus one. This one. Squares the input. That's not terrible. I'm trying to think of one that we could do that would make sense. But anyway, the examples that they have here are essentially the reason that we use sub-functions, so putting functions within functions, is usually when we're trying to do something that's quite complex mathematically. For example, integrating a function over some interval. Integrating a function over some interval finds the area under the curve of that function, right? And it's mathematically, it's a fairly complex process. There's several steps involved. So instead of trying to write it all as one piece of code, and these steps are iterative, so you do them over and over again, right? So instead of writing it as one piece of code and becoming this big piece of bloatware, you write those things that are done over and over again as little functions within the function. And then you use those functions over and over again in an iterative fashion within the main function that does the whole thing, right? So that's the idea behind that. The chance of you needing to use one of these to do something like this anytime soon is very, very low. I don't think that I give you any homework with sub-functions. Maybe I do. I don't remember ever doing something like that. Problem says you asked to create. Okay, so we do a very simple one. I think I gave you 615 to do, where you actually make 3 temperature conversion functions like you did. I think I asked you to make 3 functions actually, and then I actually ask you to put them all into one function as 3 sub-functions, but it's not really anything complex. So the big difference between the sub-functions and functions, the way they're written, is that a sub-function, when you write a sub-function, you use this same architecture of writing the function, except you remove the end here, and it just looks like this without an end on it. And then you write another one and another one and another one. And at the very beginning, you will have, so the whole thing will be put into one file. You'll have multiple functions within this file, but there will not be an end, or an end anywhere in this. It'll just be 3 functions within this thing. And I mean, that's really the main difference there. So it just allows you to do many things within a single function.
So it's not, I mean, it's not terribly difficult to write these subfunctions, except for the fact that when you're using them, you're usually doing something very difficult to begin with. So and that's why we don't want to mess around with them too much, because we don't want to get into a mathematical situation that we don't understand, trying to program a mathematical situation that is difficult. I wouldn't even run through the integration example, because it's just too messy mathematically to really be a good teaching situation for this class. So we're not going to mess with it, but that's the idea of it. And that actually takes us to the end of the chapter here. We're done with the idea of creating functions. Now the homework this week is different, because we are doing these functions things, and every homework problem, you're gonna have to turn in a different file, a different function, in other words, right? So instead of writing a program that I'm gonna be going through step by step, you're gonna write a function that I'm gonna plug something into. I'm actually gonna call your function. So you need to name your function in a good way, name it the way they tell you to name it in the homework, for example. You need to make sure that it's accepting the correct arguments, and that I can just, so if you save a file to your homework that's called temp or something like this, I should just be able to put temp into my folder right here, your file right into my folder here, and just say temp and whatever number, temp 45, hit return, and it gives me what I want. It gives me what your file is supposed to be doing, right? That's the only way. That's the only thing I should have to do. I shouldn't have to open it and look through it and try to plug things into it. Of course, I am going to open it to see, what you did, and see if there's, if you're using good program style or that, whatever, if you're annotating. And I apologize that I haven't gotten any grading done. I've been rather busy, but I'm going to start grading and giving you feedback. But from what I've seen so far of you guys getting help on your homework, you're doing pretty well, so I'm not too worried.
Professor, just with those functions, like for example, today on the whole class again, then go like make a function and then name function, say function. How I did it today in the class, I put all the functions like I did in my main folder, like today class participation. Down, I just did, I named the function
And then put it in a folder for today. Yeah.
Do you want like for homework to be done that way, or do you want like to make a folder?
It'll look like this. So when you open up your programming assignment this week, it will look different. So for problem number 2, you're gonna have just this for problem number 2 alone. You'll just save your function to here. So your
function, say the function in there.
one function per problem.
Oh, okay.
And then this one's for well, I put 2 of them for problem 2. That's not right. So apparently you get to do 2 twice and get, grades twice for number 2. But this one's for number 3. This one's for number 6, number 7. Each number now has its own place to submit your function file.
But is this okay with class participation? Because I don't think you can understand it. So then, like, you always made a function, but what I did, like, I have a code here, and I just put all the functions down here because it can call.
Yeah. So, and you can
Second way to do it.
yes, you can do functions that way, but I want you to save them in individual function files, because that's actually more efficient. Okay. Yeah.
But
So,
is this working today for just class participation?
yes, for class participation, that's fine.
Okay, but for homework,
Yeah.
okay.
For your class participation files today, it can all just be written into a single script file. The functions can just be written in there. You don't have to save them as separate files. But for the homework, save each function as a separate file, a separate function file, and named properly, and pop it in there. All right. Any other questions? All right. Well, I am done. We are done a little bit early today. I'm done talking at you. And if you have no more questions, we can leave early. It looks like I've given you 8 questions or so to do. So you're going to create 8 functions, and it looks like the first 2 are a repeat. Let me see if that might be a typo. Let me check really quick. 2, 3. Yeah, I don't really think you need to do both of these, so I'll erase one of those. Chapter 6. Question 2. Let's see, how do I get rid of this? Here we go. Withdrawal. So you guys get extra 10 points for free this week. Congratulations. Well done. All right. Well, have a good one. Stay warm. Drive safe. Watch out for rolling blackouts. My car got so cold that the battery froze. Like the battery was fine, except no charge could flow through it because the acid in the battery was like gel. I had to warm up the battery to get it to start. Good night. It's been so cold these days. All right, let's stop that. End the video.